Next up, we have Nina from CMU talking about data-driven algorithm design. Here you go, Nina.
Cool. So I'll be talking about using machine learning for data-driven or automated algorithm design, and in particular about some recent provable guarantees for this, I think, very exciting area of data-driven or algorithm design. Okay, and my focus in the talk will be on combinatorial problems, so on discrete structures, so combinatorial algorithms for discrete structures. So the way I think about it is like using machine learning and learning theory to influence theory of computing and algorithm design, and hopefully the corresponding application areas. Okay, and let me start with some very high-level motivation for this line of work. So the classic way to design and analyze algorithms for combinatorial problems impose that the algorithms that we design for a given problem will be used to solve worst-case instances of the problem about which the algorithm has absolutely no information at all. Okay, and so in this classic framework, the kind of performance guarantees we seek for our algorithm is that the algorithm would succeed even for solving a one-time worst-case instance of the underlying algorithm problem. Okay, and so within this classic framework, we'll know there are some problems that are easy. So for example, if we are concerned with running time as our major performance measure, we know that there are some problems that we teach in basic undergraduate algorithms courses for which we have optimal polynomial time algorithms that are guaranteed to output the optimal solution in polynomial time, even on worst-case instances. Okay, so there are some problems that are easy within the classic framework, but for most problems within the classic framework, we do not have such strong performance guarantees. Okay, so examples of hard problems include clustering problems, partitioning problems, subset selection problems. In fact, actually, most combinatorial problems are kind of hard within the classic framework. Now, one interesting approach commonly used in practice for such hard problems, especially in cases when we need to solve not only one instance of the underlying algorithmic problem, but in cases where we need to repeatedly solve instances of the underlying algorithmic problem. So one kind of interesting approach used in practice to solve these hard problems is to use machine learning and instances coming from the given domain in order to learn an algorithm that does well just on our type of instances. Okay, and this is very natural idea, of course, because in practice, for a given type of combinatorial problem, different methods work better in different settings, and also we often have large family of methods that we could choose from. So it's very natural to try to use machine learning and instances of the problem coming from our specific domain to learn an algorithm that does well just on our type of instances. Okay, and indeed, this approach has a large history in many applied communities, including in the AI community. Like Eric Horowitz actually had some early work on this. Also in computational biology community, in a kind of AI-based mechanism design community. So this idea of using machine learning to learn algorithms has been widely used in many different applied communities, and actually several breakthroughs in these areas have come from this approach. Okay. However, surprisingly to me, until basically very, very recently, we knew very little formally about this approach. Okay, and so my talk today, I'll try to survey some recent work that we've been doing with my students and collaborators in order to kind of provide formal guarantees for this data-driven algorithm selection.
Formal guarantees for the performance or correctness, or both?
So I'll discuss. Yeah. Will be, like, of course, we're going to use distributional learning formalization or online learning formalizations, and the actual meaning of the guarantees will depend on the specific formalization. Okay. And I'll mention several case studies, but also I'll try to kind of hint towards kind of more general principles that arise by thinking about these problems, hopefully more broadly applicable beyond specific cases. Okay, and because this is also a lot of the people here in the audience are AI and machine learning, I just want to point out, obviously, that this is very connected to a bunch of very hot topics in applied machine learning these days, like hyperparameter tuning, AutoML, meta learning. Of course, this topic is very related to those topics, except that think about it, about our setting being in combinatorial settings, and also we have provable guarantees as opposed to a lot of these topics in more applied ML without guarantees. Okay, so that's a kind of a high-level overview, and And with this, the kind of structure of my talk is as follows. I'll describe how you can think about data-driven algorithm design or selection as a distributional or statistical learning problem. I'll mention a couple of case studies and also point to a general sample complexity theorem that arises in this context. And I don't think I'll have a lot of time to talk about online learning, the online learning formulation, but I'm happy to talk offline about details of that formulation. Okay, so I'll start with the data-driven algorithm design as a distributional learning problem. But before doing so, let me just to be concrete, let me mention an example of a problem that we might want to solve in a data-driven approach. Okay, and this is a very familiar problem to all of us. That's clustering. We are given a set of objects like news articles, web pages, search results, and we want to somehow cluster them into natural groups as well as we can. And what I want to point out is this is a perfect example of a problem where we need to repeatedly solve instances of a given clustering problem, right? So, for example, if you are Google and if you are using clustering to cluster news articles, then of course you're gonna cluster news articles every day, in fact, many times a day. So this is a perfect example of a problem that we need to solve repeatedly. So we can try to hope to use a data-driven approach. Okay, and of course, like formally, like what type of clustering technique would be using? We can either use objective-based clustering, right, where we pick a specific objective function like the k-means objective, the k-median objective, or the center objective, and try to optimize it on a given input set of data points. So this is one formulation you can try to use. And of course, we all know that this, for example, all of these specific objectives like optimizing k-means, optimizing k-median, and so on is NP hard. So it makes sense to try to use a data-driven approach to kind of learn a good algorithm for our type of data, because there is no universal efficient algorithm that works all on worst-case instances. Okay, so objective-based clustering is a good application of the data-driven approach. But if you think about it, also kind of the more machine learning formulation, where somehow we assume that there is a hidden ground truth and we are trying to get close to it, kind of unsupervised learning or matching the ground truth version of the clustering problem, also makes sense in this data-driven approach. So either of these formulations can be casted as data-driven algorithm design. Okay, so now with this example, now we can go and describe how we can think about algorithm selection is a distributional learning problem, and of course this will be super familiar to the machine learning people here in the audience. So it's very natural. So what we do, we fix an algorithmic problem that we want to solve, like facility location or clustering or your favorite combinatorial problem. Then we fix a large family of algorithms for our problem, and this can be a parameterized infinite family of algorithms, right? Because it might have various modules. An algorithm in the family might have various modules with knobs that you might have to tune. Right? And we fix this family of algorithms because we either know it works well in practice or maybe because we have analytical reasons to believe it might be good for our type of data. Okay? And then what we do, we take a sample of typical instances of our problem coming from our domain, and technically we assume that this sample of typical instances is an IID sample of typical instances from some underlying distribution of our instances. And we use this sample of typical instances to come up with a new an algorithm that we hope or we want to prove it as well as new instances coming from the same underlying source. Okay? So for example, and so by the way, I'm using this pictorially, but this is hopefully very clear. So for example, if we are doing, say, facility location, what are these typical instances? Well, the first sample could be an input graph, first input graph, a second sample will be a second input graph, and so on, right? Or if we are doing clustering, if we are trying to learn a clustering algorithm, say, to cluster documents, then what are our typical instances? Well, a first instance could be a first set of documents, a second instance could be a second set of documents, and so on. And this either can be unlabeled if we are trying to maybe do, say, objective-based clustering, like k-means clustering, or they can be labeled if you are trying to match ground truth. So for example, if I'm trying to cluster the documents as ADIs clustering documents, and of course I need, for the training examples, ground truth clusterings. Okay? And so basically, based on this set of typical instances, what we want to do, we want to come up with an algorithm that performs well, that we can prove that performs well on new random instances coming from the same underlying distribution of typical instances as the training set. And of course, we now know that we can build on tools from statistical learning theory to kind of analyze sample complexity questions in this framework, meaning to analyze how large should the set of typical instances be in order to guarantee that if we output an algorithm that does well over the training set of typical instances, that algorithm will also do well on new instances that we've coming from the same source, but we've never seen the training set. Okay, and of course, we also know from statistical learning theory that in order to analyze these sample complexity results, for example, in order to get uniform convergence sample complexity results, what we need to be able to understand is a kind of the intrinsic dimension or the intrinsic complexity of the induced class of functions by the family of algorithms and our performance measure at hand. Okay, so all we need to do is to analyze the pseudo dimension or the Rademacher complexity of this induced class of functions. And then, of course, that's a key quantity in our typical uniform convergence bounds. Okay, now what's interesting in this new domain, and I find it's exciting from a learning theory point of view, is that the functions that appear in these settings, once you start learning algorithms, because our hypothesis space is a space of algorithms, now we get very interesting structures. So in particular, because we are learning algorithms for combinatorial problems, we essentially, and our corresponding algorithms have combinatorial modules, we get in situations where if we slightly change the parameters, we can get drastically different outputs. So kind of the corresponding cost functions have sharp discontinuities. And so it's kind of interesting to try to analyze notions of dimensions in these scenarios. Okay, so that's kind of, I would say, what makes these problems different from more classic statistical learning theory. Okay? And we'll see a couple of examples of this form. These are the specific types of functions that appear in the various applications we looked at. Okay, cool. And so this is the statistical learning form. I want to actually point out that this thinking about algorithm design or as a distribution learning problem was actually introduced in a paper by Tim Ravgarden and Rishi Gupta, his former student Rishi Gupta, in a paper that appeared in ITCS and then in SciComp. And they proposed a model, viewing algorithm selection as a distribution learning problem. And then also they analyzed parameterized families for of greedy algorithms for subset selection problems like knapsack problems in that work. Okay? And I found that paper fascinating. I'm surprised nobody has written such a paper earlier because it's very natural and I think it's very powerful as well. And after that, with my students and collaborators, we followed up on it and we analyzed new algorithm classes for a variety of combinatorial problems. Okay, and I'm just going to quickly mention some of them, and then I'm going to go into details of a couple of them. Okay, so for example, in our first paper on the topic, we looked at, in the context of clustering problems, we looked at parameterized linkage procedures for clustering, followed by some, say, a fixed type of post-processing. Okay, also also for clustering, in a new riff paper last year, we looked at infinite families of Lloyd's method, in particular parameterized families of Lloyd's method, so learning to initialize the Lloyd's method. Okay, more recently, with some colleagues from computational biology at CMU, we looked at parameterized dynamic programming procedures for solving alignment problems in computational biology, like sequence alignment. And so these are some types of combinatorial problems we looked at. We also looked at, in the original paper, at a very different type of family of algorithms. So, for example, if you are trying to solve partitioning problems that can be written as integer quadratic programs like maxcut, we looked at parameterized families. We looked at families of algorithms that reduce semi-definite programming, followed by some sort of parameterized rounding, and again learn how to round for our types of instances. Okay, and in all of these examples that I've given so far, actually, by design, to go back to your question, the algorithms that we look at, they are by design polynomial time. And what I'm trying to learn is an algorithm that has good solution quality, like it has a good value of maxcut or clusters the documents well, or maybe aligns the sequences well. Okay? But we also have looked at types of problems where, like, for example, we looked at solving mixed integer programs via branch and bound, which is a type of technique widely used in AI and OR. And here, these algorithms, the algorithms in this family solve the problem to optimality, but they might take a long time. And so we're trying to optimize for its running time. So the solution quality for the algorithm is running time right now. Okay? And we also looked at very related techniques also appearing kind of in the context of automated mechanism design for multi-buyer, multi-item scenarios. And again, here we looked at families of mechanisms like parameterized VCG auction, posted prices, and so on. And here, we are optimizing for is revenue. So like the revenue, really the solution qualities of these families of procedures. Okay, and so it turns out actually after looking at all of these, some general patterns emerge, and I'm going to tell you a little bit about those. But before doing so, just to be concrete and to have a concrete example in mind to think about, I want to give you a simple example of a family of parameterized algorithms for clustering problems. Okay, so in order to take a data-driven approach for clustering problems, the very first thing we want to do is to put down, of course, a family of algorithms. And here is a simple family of algorithms that we looked at, both because it's kind of widely used in practice and also because it has some nice analytical properties if the data is extremely nice, like stable type of instances. Okay, it's known from like beyond those case analysis branch in theory of computing. Okay, so the family of algorithms is as follows. It's extremely simple. We have two stages. Each algorithm has two stages. We first use a bottom-up linkage procedure to greedy procedure to hook up the data into a hierarchy to create a cluster tree. And then we just do a fixed post-processing on this tree. For example, we can do dynamic programming to extract the best k-means clustering, or we might just output the clusters induced by the last k-merges, or we just might output the hierarchy to the user, and the user can look at it. Okay? And of course, and so just to remind you, what does it mean bottom-up agglomerative linkage procedures? What we do is we start with points in their own little cluster, and then we repeatedly merge the two closest clusters. Okay? And of course, different definitions of closest will lead to different algorithms. So for example, here, different definitions of closest between pairs of, between subsets of points lead to different algorithms. So here is an example of a classic algorithm we teach in basic undergraduate machine learning courses, single linkage, right? Where we define the distance between two subsets A and B to be the minimum distance between the points in the two subsets. Right, so here I'm assuming the distance between base points is fixed. And so single linkage defines the distance between the two subsets to be the minimum distance between points in the corresponding subsets. But another classic algorithm, complete linkage, defines the distance between the two subsets to be the maximum distance between the points in the corresponding subsets. Right? And so you can even imagine now coming up with an infinite family of linkage procedures because we might want to interpolate between these base criteria. Right? And so, for example, here is an example of a family that we looked at in our work, something that I call alpha-weighted linkage. Right now, there is a parameter alpha that I can hope to tune for my data. And I define the distance between two subsets A and B to be 1 minus alpha times the distance given by single linkage plus alpha times the distance given by complete linkage. Okay? So this is a concrete example of this alpha-weighted linkage family is a concrete example of a parameterized family of algorithms for a combinatorial problem clustering. Right? And we can now start to understand what the pseudo-dimension of these families of algorithms is. And by the way, what pseudo-dimension is just the most natural extension of VC dimension to real valued functions. I'm not going to define it precisely, but that's all you need to know. Okay, and so for this specific family of algorithms, I'm going to quickly show you that the pseudo-dimension is only log n, or n is an upper bound on the number of points in any input instance that I might have to solve. And because the pseudo-dimension is log n, actually, you can also show that actually if you are given a set of typical instances, a training set of typical instances of clustering problems, we can find the best algorithm from this family in polynomial time. Okay, so you can, in other words, in machine learning theory term, you can just solve VRM in polynomial time efficiently for this simple family of clustering procedures. Okay, and like in any of these combinatorial problems, kind of the challenge here is really because of this, as I mentioned, because of this combinatorial kind of type of output. You can be in a situation that if you slightly change alpha, this can lead to a kind of to a change early on in the decision made by the linkage procedure, which then can snowball and produce a much larger change later on. So in other words, if you slightly change alpha, you can get a totally different output. And so this is really the difficulty here. But you know what in order to analyze, what we can show is that this doesn't happen too often, really. Okay, and so this then leads to good pseudo-dimension bounds. Okay, and in particular, what we can show is that Here's the key fact that kind of implies that the pseudo-dimension is only logarithmic in n, where n is an upper bound on the number of points in the input instance. So the fact is as follows. It's basically what it shows is kind of that the corresponding cost function is piecewise constant. Okay, so what does it mean? Well, for any given value of alpha, when you run alpha weighted linkage, kind of the algorithm is going to make a sequence of decisions and it's going to create a specific linkage tree. Now, of course, if I change alpha, I'm going to get a different tree. But what this fact here says that if I vary alpha from, say, 0 to 1, and if I fix an instance, a clustering instance of n points, and then I vary the parameter alpha from 0 to 1, there are at most n to the 8 switching point where the tree produced on the instance changes. And then, of course, this then implies that no matter what is your cost function on the top, distance to the ground truth or k-means cost and so on, the corresponding cost function is piecewise constant with n to the 8 pieces. Okay? Which turns out to be very nice because then implies that the pseudo-dimension is only log n. Okay? And let me just quickly give you a high-level idea of how this fact is proven. This is not hard at all in this specific case. So the key idea is as follows. So if you fix a clustering instance, and let's even fix alpha, which is a parameter in my alpha weighted linkage procedure, and let's imagine that at some point in the algorithm has to decide, should it merge the blob n1 and n2, or should it merge the blob n3 and n4, right? Now, the decision here depends on 8 points, because if I denote by p and q to be the farthest points in n1 and n2, it will give the distance given by complete linkage, and p prime and q prime to be the closest points in n1 and n2. And if I denote by r and s to be the farthest points in n3 and n4, and r prime and s prime to be the closest points in n3 and n4, the decision on whether to merge the first two blobs, n1 and n2 versus n3 and n4, really depends on which of these two quantities, alpha times the distance between p and q, plus 1 minus alpha times the distance between p prime and q prime, or alpha times the distance between r and s, plus 1 minus alpha times the distance between r prime and s prime is smaller and bigger. And if you think about it, like a critical point where the behavior of the algorithm switches is really at the moment where we have an equality here, right? So in other words, a critical point really happens at a root of a linear equality like this, or the linear equality is given by 8 points. But of course, I only have n to the 8 such kind of linear qualities that I can put down because I have, this is the number of 8 supers and out of n points. Okay, so this basically proves that kind of at a high level, it's the key idea for proving that for this specific simple linkage family, if I fix alpha, if I fix the instance, the clustering instance, and vary alpha, I can only get n to the 8 clustering trees produced. 10 minutes, great, that's good, that's perfect. Good, yeah? And now once I have this structural result, I can immediately prove the pseudo-dimension bounds, right? This is here what I showed you, what happens if I fix the instance and vary alpha. I showed you what happens with the corresponding cost function. But of course, when you compute the pseudo-dimension, you care about not only about the behavior of the algorithm family on a given instance, but you kind of care about how many instances can you shattering crazy. How many instances can we really get an exponential number of behaviors, right? This is what we care about. And so now I have to think about what happens if I have m instances, m clustering instances. And what I know, the immediate key, the fact on the previous bound immediately implies that if I have m clustering instances, as I vary alpha, I can only get like m times n to the power of 8 patterns produced on these m clustering instances. And now I just use the definition of pseudo-dimension, roughly speaking, to then just compute what the pseudo-dimension is, because the pseudo-dimension will be the largest term for which an exponential number of patterns is achievable. Okay, and so all I have to do is to just solve for the largest term for which I can achieve an exponential number of patterns. So that means I have to solve this inequality over here. The largest term for which 2 to the m is upper bounded by m times n to the 8. And so this then immediately implies that the pseudo-dimension is only log n. Okay, for this simple example here. By the way, I don't have this on my slides. You might ask, do you gain anything in practice for doing this interpolation? It turns out that actually you can. So I had a master student who did the experiment. It turns out that, even on MNIST, when you try to class a subset of MNIST, actually you can gain a little bit by tuning the parameter alpha here in the alpha weighted linkage, like a 3%. So not a lot, but you still gain a 3%. And when you create artificial examples, so you gain a lot. Okay? But here is another family also staying with clustering, where we gain a lot in practice. Oh, sorry, actually, before going there, let me just finish off, right? Because I just showed you is that the pseudo-dimension of this family of alpha-weighted linkage procedures is log n, only a big O of log n. Actually, by the way, we can also show it's really big theta of log n. One of my former students had lower bounds showing that. Moreover, you can also implement, you can also solve the corresponding ERM problem in polynomial time. So if I give you a set of instances, of typical instances, you can find the best alpha from the family in polynomial time. One kind of more inefficient way to do it, but still polynomial time, is to, given every input instance, you compute the corresponding alpha interval of that instance. You take all the union of all those critical points and try to take the best over on average over the sample. That works. You can even make it more efficient. And one of my students did that and ran experiments with it. And as I mentioned, by doing this on a MNIST, for example, you get a 3% improvement over either single or complete linkage. And also on some syntactic datasets, you can do even better. Okay? But here is actually also, and this is, by the way, I'm not saying, but this is really kind of, for me, it was really a toy example to try to understand this space of like, how do you analyze data-driven algorithm design from a learning theory point of view, but we also done experiments just for fun. I'm not advocating it as the technique to use when you try to do data-driven clustering. But actually, another family where you can slightly improve you can do even a little bit better experimentally, and this actually can be also of interest experimentally, in addition to being of interest theoretically, is one where you are not tuning only the alpha, you are not only tuning kind of the linkage procedure, but you are also tuning the distance function. Okay, and in particular, for certain types of data, you might have very different types of distance information. So for example, if you have captioned images, of course, we can use some distance function based on the pixel information of the image, but you might also have a very different distance function based on the captions, right? And you can try to mix between those. Or similarly, for handwritten digits, for example, for the classic omniglot data set that is used in meta-learning, you have both the pixel information, but you also have stroke data about how the characters were written. And so this can provide very complementary type of distance information. And so now you can put down kind of an infinite family of matrix or distance functions where you interpolate now, say, linearly between these, say, for now, two base distance functions, d0 and d1. And so you can now try to tune also this beta parameter related to the distance function. Okay, so you can, for example, get now, just to be concrete, if I can now try to get a family of alpha beta weighted linkage procedures, or I use alpha, the parameter alpha, to interpolate between the linkage criteria, single and complete linkage, and I use the parameter beta to kind of tune the distance function, to interpolate between two fixed base distance functions between pairs of points. Okay, and I'll call this alpha beta weighted linkage. And you can again try to analyze what's the pseudo dimension of this family of algorithms, and of course try to find the best kind of algorithm from this family for your type of data. And I'm not going to go through the details here, but it turns out that again, because we can still show here that kind of the pseudo dimension of this family of procedures, alpha beta weighted linkage procedure, is log n. Now the structure result is a little bit, it's still simple, but just tiny bit more complicated. So to prove that the pseudo dimension of this alpha beta weighted linkage is log n, what we have to show is, again, something about the structure of the dual function. So I fix an instance, vary the parameters alpha beta, and I can show that I can partition the space, the parameter space, with a number of linear and quadratic equations, so that for any two parameters in the same region, I get the same cluster tree produced. Okay, and once I have this, and I can again do the pseudo-dimension argument on the top of this. Okay, and I'm not going to go through the details. How many more minutes do I have? Two. Okay, so I'm going to skip the details here. But you have to look at the structure of the problem to conclude this fact. Okay, but actually before jumping to the next higher level story, I want to actually mention that this tuning alpha and beta actually did have an impact on the real world, like on real data. So for example, we've done experiments on omniglot, which is a classic data set used for meta learning these days. And here we show that if you interpolate between distance functions given by features obtained from CNN embeddings on a related data set, say MNIST, on the MNIST, trained on MNIST, if interpolate between kind of distance function given by CNN embeddings, convolutional neural network embedding, and the stroke, hand design distance function that uses a stroke information, you can actually get a big improvement, like about a 9% improvement in accuracy. So here it makes a difference. It kind of shows that the two distance functions are very complementary. And actually, my students did this experiment specifically for this workshop, but I can use the word deep learning here somewhere, because I'm using CNN embeddings. I'm actually semi-kidding, but it's true. But it's nice to see that actually does improve in practice. I was pleased with that. Okay, now going back to the high-level story, it turns out that we look, as I mentioned, look at many different other types of problems. Like we look, for example, at partitioning problems that can be written as integer quadratic programs. And here we look at parameterized families of procedures. So we do semi-definite programming relaxation, followed by like randomized rounding, and this is parameterized rounding. Not going through the details, the key point to observe here is that like to prove the pseudo-dimension bounds, what we have to show is that if we fix an instance and vary the parameters of the underlying algorithm family, the corresponding function is piecewise structure. So in particular here is piecewise inversely quadratic with only n pieces. Okay, so what happens here? Related structure appears when we do mechanism design. So for example, if we look at, so just to be concrete, posted price mechanisms, in cases where we have multi-buyer, multi-item scenarios, and now we have a parameter for each posted price we might set on each of the items. And again, what arises here is that kind of the corresponding, if I fix an instance, so a set of bidders and their values for the subsets of the items, if I vary the prices, the corresponding revenue function is piecewise linear, where each of the pieces in the parameter space is given by a linear separator, intersection of linear separators. Okay, and so this was kind of the key resolver to use to prove the pseudo-dimension bounding that work. And so motivated by this, now in most recent work, we wrote a more general theorem trying to kind of decouple the structure of the problem from what we need to get statistical kind of pseudo-dimension bounds. And here is the abstraction. So what we really care about is computing the pseudo-dimension of a function class parameterized by alpha, where each function is parameterized by alpha, and takes as input instances of the problem, like, say, clustering, a set of I want to cluster. Okay? And so this is what I want to bound the pseudo-dimension of such a function class. In all of these proofs, we take advantage of the structure on the dual class of functions. Now, a function, the dual class, is parameterized by an instance of the problem and takes as inputs possible parameters values. And what we showed in all of these domains is that these dual functions are piecewise structured. And what do we mean by piecewise structured? For every function that in the dual looks like this, I can basically partition the parameter space by using functions from a well-behaved function class F, such that inside each of the species, like here, the corresponding cost function is identical to a function G coming from another function class, capital G. And what we are able to show is that basically we can give a bound on the pseudo-dimension of the original function class that I really care about, where the function, the class is parameterized by alpha, as a function of the kind of the niceness of these dual functions. And again, the niceness here is these dual functions are piecewise structured, where the pieces are defined by functions from a function class F, and inside is the piece I'm identical to a function G from a function class G. And you can put a bound on the pseudo-dimension of the final function class I care about is a function of the niceness of these function classes F and G, a function of the boundary functions F and the functions, the niceness of the function inside of the space. Okay, and one kind of cool fact that appears here is not really the BC dimension of those function classes, but it's the BC dimension of the dual of those function classes. And there are reasons for that, and they can discuss about it offline. Okay, and just I have, I guess, 0 minutes left. I just want to mention that so far I talked about distributional learning. You can also ask questions, how about online learning? Think about algorithm selection as an online learning problem, where the instances are not given to you up front, but they come one by one, and you kind of want to achieve no regret. And because, as I already mentioned, now we have sharp discontinuities. If you, I think as many people here are online learning experts in the audience, you know that once we have sharp discontinuities, it's impossible to achieve no regret. And so we had a paper with my students in Fox 2018, and the follow-up paper where we identified sufficient conditions for achieving no regret once you are doing online learning of piecewise Lipschitz functions, and then show that these conditions hold in many of these algorithm configuration or online algorithm selection problems. Okay, and again, I'm happy to talk about this offline. The condition is just on this piecewise efficient function is just dispersion. Roughly speaking, we just require that the discontinuities of the corresponding cost function don't concentrate too much. They are dispersed. And you can put formal definitions around that. And again, I'm happy to talk offline. Okay, but I guess just to summarize, so I think this is a very interesting area of research to think about algorithm design as a learning problem, either distributional learning problem or statistical learning problem or online learning problem. And you can provide strong formal guarantees. And also, from a learning theory point of view, the structures that arise in these settings I think are very interesting and kind of help us push the boundaries of learning theory as well, which is always very exciting. So thank you.
Just a quick comment.
Sure.
I think that if I understood your problem correctly, I can reduce the n to the n to n squared.
I think we have a lower bound, n to the fifth. So we can
So
show.
let's discuss.
So yeah, so actually the lower bound that we know is n to the fifth. We can show an instance, or n to the fifth. You can have n to the discontinuities. Yes. We don't know if there is a gap between n to the fifth and n to the eighth. Now, that being said, one of the experiments that my students have done in the real world, you never get n to the fifth, but the instance is very convoluted. In anything that we've tried, it's all linear in n. So that's why you can even tune the parameters for those combinatorial
It's something in your model because I'm pretty sure that in my approach, n squared is the right.
Let's talk about it.
Okay, next up we have Costis from MIT.
So I'm going to talk about machine learning bias and how to use truncated statistics to reduce the bias. And in particular, so the motivation of this talk is that oftentimes in data science problems, you work with a data set, and oftentimes collecting the data set. There's a selection bias in collecting your data, which makes the training set that you use to train your models different than the test set, the conditions that your model is going to be facing in the future. And in particular, training on a biased data set will introduce bias in your predictions. So the goal of the talk is to decrease this bias using censored and truncated statistics, which refers to an area in statistics that is trying to do inference given truncated or censored samples. Truncated samples refer to the situation where samples falling outside of an observation window are not observed and their count is also not known. Censoring means you at least have the count of how many data fall outside of your observation window. And of course, this can happen for many reasons, these types of phenomena. Possibly your measuring devices, your measurement devices get saturated outside of a band of measurement. So when they get saturated, you get bad readings, and these are not reliable. So that's a case of censoring. You know how many measurements are reliable, and you also know how many aren't. Or it could arise from bad experiment design, or it could come from situations where ethical or other legal considerations preclude you from using some data points in your inference. So let me give a couple of motivating examples that show what may go wrong if you have bias in your data. So the first one is a well-discussed question in econometrics since the 50s. That has to do with relating IQ training and education to earnings of people. So several works in the 50s and 60s tried to understand this model by collecting data, and they did what you would think is the right thing. So they surveyed families whose income is 1.5 times the poverty level. And they collected data where the covariates correspond to the IQ, training, education, and a bunch of other features of individuals, for example, belonging to unions, etc. And the response variables were earnings for those individuals. And they tried to fit a model. In particular, they tried to fit linear models to their data. And the issue that might appear to be important is that thresholding your data collection to families whose income is 1 point below a threshold may actually introduce bias in which features you think are important for income. And in particular, later works debunked the results of prior work, showing, for example, that besides education, occupational training and IQ are actually important in earnings, where previous work found that mostly education is important for earnings. Okay, so prior work who did not take into account the thresholding gave incorrect conclusions about what is important for earnings. So to maybe feel the issue more viscerally, here's a different example. So suppose instead of doing IQ versus income, imagine I try to understand the importance of height to being a good basketball player. And imagine that because I'm being lazy in my data collection, instead of serving the whole population, which is of course hard, I instead decide to download the NBA data to do that. So it's quite possible that if I try to fit a model on the NBA data, I may conclude that height is actually neutral or even negatively correlated to basketball performance. But that incorrect conclusion comes from the fact that I was lazy and I downloaded the NBA data as opposed to serving the whole population. And the mental picture I want you to have while I'm going through my slides is this, that, for example, in vanilla linear regression, you assume that the world is a perturbation around a line. But if you went and thresholded the data, say you only observe, say this is Y is basketball performance and X is height, it could be that the world is linear around some, like a perturbation of a line. But imagine that I went and downloaded NBA data, which in particular means that I only look at people who have good basketball performance above the threshold. Now, it's quite likely that if I try to fit a line on that data, these lines look much more plausible for this data set than this line. Okay?
Is here independent of the Xi's, or are you thinking of this as additive noise, or?
Say, that's just an example. But like our standard, like least squares regression is a good estimator for a world that is where the response variable is just theta times x plus some zero mean noise, like Gaussian noise.
Okay, this shouldn't happen if it's additive noise, as long as you choose the x's independent of the.
It happens so even if it is additive, right?
Wait, if you choose it, but you need to choose based
suppose
on the
that
y's.
truth is constant. You only estimate the mean.
Yeah,
He's choosing based on.
You're choosing based on the y's. But in terms of the x's, if you choose it, then you're fine.
Oh yeah, so you're asking what happens if I truncate based on an x variable?
Yeah, then you're.
I'll get to an example like in the next slide. So here I'm talking about y truncation. There is also x truncation. That's also an important problem. I'll get to that in a sec. But as far as y truncation is concerned, we see here that I believe the way my believed line turns is because, like this data point should not be in. This is a short guy who happens to be a good basketball player because of noise. So he makes it into NBA, and he makes me believe that short guys are good basketball players. Okay, but that was a result of the noise, which made that guy enter into my data set. So coming to the X truncation, a well-discussed phenomenon observed recently with gender classifiers is that while gender classifiers trained on internet data are really good in predicting genders of basically light skin tone people, they can be very bad in people who are not as much represented in the data set. So in particular, several of gender classifiers, from Microsoft, Facebook, etc., were pretty bad in darker female gender prediction. And the explanation that has been offered for why this happens is that internet data has much more male, Caucasian, lighter skin tone people. And for this reason, when you train on the data set, you pay less attention to other people. And when you then go and test the gender classifier in a particular subpopulation, you may actually get bad performance. Okay? And that's an example where you have some truncation in the X, covariates, and which leads to you not paying enough attention to some subpopulations. So what I want to do is I want to see how ideas from truncated statistics can be used to fight these kinds of biases from entering your predictions when you train on biased data sets. And I want to give a flavor of some of the models and the work that I've done with several collaborators. And I will center around 3 problems. So one pertains to the truncation on the y variable, another truncation on the x variable, and then the third one is going to be an unsupervised learning setting. So problem number 1 that I want to consider is the following scenario. And that is supposed to capture situations like IQ versus earning and height versus basketball performance. So I want to imagine that the factory that produces my training data is the following data factory.
Can I ask one question about the gender classification example?
Yeah.
So there, it's quite possible that this is not. I mean, the main issue there is not truncation, right? It's because maybe this is also the test data set. The data that So the point is, this is doing well on the training and maybe the training and test data both have underrepresentation of some class.
Yeah.
So
This is the class conditional errors.
Yeah. So if the training data set is representative of the test data set, then then you're doing a good job. There's no truncation that biases your predictor.
No, it just means that your loss function doesn't include an aspect of fairness that a small portion of the population should be also well represented.
Yeah, that's not a matter of truncation. So the first problem that pertains to truncation on the y-axis is assumes the training set is produced by the following data factory. So first, you sample x's from some underlying population of x's. Then a response is computing for every x. The response is a parametric function plus noise. Noise could also come from a parametric distribution. And then, so up until this point, this is the classical supervised learning situation where you have IID data, training distribution is the same as the test distribution, and life is good. What is different here is that then you look at the y and you decide whether or not to include it in the training set. So you look at the y. So for example, you look whether this guy is a good basketball player. And if he's a good basketball player, you put him in the NBA data. Otherwise, you just throw that sample in the trash. Okay? For this scenario, we'll assume that I know this truncation phi. Okay? And it could be probabilistic. Okay, so what I don't know is I don't know D. I don't know the Bayes distribution that samples humans. I don't know the mechanism that relates humans' features to how good basketball players they are, and I don't know the noise model. But I do know phi, because phi, in some sense, I control. So I chose to download the NBA data, or in the IQ versus earning example, I chose to go and focus in that particular neighborhood and do my survey there. Okay? So just to see whether that model captures the scenario of truncated linear regression. So in that case, the model is a line, the noise is Gaussian, and my truncation is just deterministic. It's a thresholding that hides data whose y is below a certain threshold. So the goal, given training data produced by this factory, okay, the goal is to recover the underlying theta, the underlying parameters that determine the mechanism. So the results that we have with Goulakis, Damos, and Zabetakis, and with Andrew Ilias, who is here, Suchitra, and Manolis Zabetakis, are of two kinds. So it's a general framework that allows you to learn models in these kinds of scenarios. And also, so this is a general SGD-based framework, which you can ship to a GPU and try to recover thetas. Now, that general framework, if you restrict in truncated linear regression or a truncated probit or logistic regression setting, it will give you end-to-end guarantees about recovery of the underlying parameters. So it's a framework that can be used either for a well-behaved setting where you can get end-to-end guarantees, or it can be used in an arbitrary setting. It's an SGD-based framework that you can run. But of course, if you have a neural network here, you will lose the end-to-end guarantees, but you can at least run your algorithm. Okay? So just to compare our results with prior work. So there is a long line of research in econometrics, statistics, and statistics on truncated or censored regression, either linear or probit and logistic. And the technical bottlenecks in that work are of two kinds. First, and these technical issues arise in high-dimensional settings. So the first one is the algorithms that are used are inefficient, and importantly, the convergent rates of the methods have bad dependencies on the dimension. Okay, you get this 1/√n rates that you expect for maximum likelihood, but the dependence of the rate in the dimension is not well understood. And so what we get is we get optimal rates, namely the same rates that you get for untruncated regression. We get efficient algorithms, and we allow arbitrary truncation sets. They don't need to be thresholds. They can be basically any measurable set.
What is the dependence on the thresholding function, on the truncation function? There needs to be something.
Yeah. So the selection function, the phi function, can be any measurable function. To get these rates, you need two things. So one is the standard thing you need for linear regression, which is that the empirical covariance matrix of your xi's has singular values that are lower bounded. This is the standard thing you need for linear regression. The extra assumption you need for truncated regression is that the thresholding does not basically obliterate all of your data. That the average xi has a constant probability of not being obliterated by the thresholding. So as long as you have some 1% on average probability of making it into the training set, you get these guarantees. Okay. So I wanted to give a sense of the techniques of, and these are sort of representative. Oh yeah.
So you're assuming that what fraction is getting truncated here? Because you're getting an n here, so.
N is the number. Oh, n is the.
It's the non-truncated.
N is the number of successful data points. So
okay.
How many people were surveyed in that neighborhood?
But that's not the only thing. There has to be also some dependence on this epsilon.
What is epsilon?
Sorry, just the probability that the fraction of the probability that an average data point is.
Yeah. So that's. We assume it's a constant and it's in the order notation. Yeah. Yeah. So let's assume that every data point has a 1% probability of making it into your observation window. That suffices. It's not you can get weaker conditions, but let's say that each xi has a decent probability of making it into the training set.
And by that you mean condition like before you see the y, it has a chance of making.
Correct. Yeah. So like
Phi of x.
like if you look at this picture here, so say my threshold is here. I want that any x has a decent probability of making it into the say 1% probability of making it in here. I don't need for every x, but I need for the average x.
So phi is actually just a threshold. It's not some crazy function. It's a threshold function you're using.
It could be a probability, as I said, it could be a measurable function, but I need.
Okay, but it has to have this property that
Yes.
unconditionally.
Yes.
But a valid truncation function is just, for instance, remove all the points in the middle row.
Correct. It could be. Yeah. Look at neighborhood where incomes fall in a band. Right. So now, I need that the average human has a decent probability of, living in that neighborhood. Like. Right. So let me get a sense of the techniques, and these are representative of what's going on in this line of work. So I have this model for how my training set is produced. And I have to ask, I want to do maximum likelihood, and I want to ask, what is the density of my training set? So the density of my training set is a point xy. The density is something like, it has to be sampled here. I have to sample. So I'm going to restrict my attention now to like the very basic linear regression model. Okay, so you have a line, you have a Gaussian normal 0, 1. So the density of the training set is this density times the Gaussian density times the probability that y isn't truncated. And what makes this density hard is that also I have to normalize it. So there is some normalizing z, so some partition function. But the density of my training set has these three components and the normalizing function. And what I want to do is I want to do population log likelihood on this model. To recover in this very simple setting, I only want to recover theta. So the log likelihood, the population log likelihood is an expectation over the true model theta star, so this density with the true theta star, of the logarithm of all of these guys minus logarithm of the partition function. Now the partition function, of course, depends on theta, so it depends on theta star here. Now, so the obvious issue that arises is that first, so to do likelihood over here, so we don't know d, we don't know the distribution d, and but even if we did, we would have to compute this partition function, and that is hard. That's difficult. So, but the saving grace here is that even though you cannot compute the likelihood, you cannot compute the gradient, you can still get a stochastic gradient. You can still get a random variable whose expectation is the gradient of this function, without needing to know d and without having to compute the partition function. Okay? So in particular, it's not hard to see that the gradient of this population log likelihood function becomes the difference of two expectations. And that's an exact equality. And that's not very hard to see. So the gradient of this log likelihood is the difference of two expectations. One expectation is taken with respect to the true model, theta star, of this expression. The other expectation is with respect to the theta, where I'm trying to compute the gradient. So in particular, if I want to get, right, so the gradient, the gradient gets rid of this guy that I don't know. The gradient makes this, gives me this term, the gradient of this guy gives me this term. And the claim, and that's not hard to see, is that the gradient of this guy with respect to theta, so z depends on theta, is just this expectation. Okay, that's not hard to see, and that's very standard, that the gradient of the partition function is an expectation. Okay, so in particular, the gradient of the whole thing is the difference of two expectations. One expectation is of this variable with respect to a sample from the true model, and the other expectation is of the same function, but on a sample from the model for the particular theta where I'm computing the gradient. So, yeah. So I want to do stochastic gradient descent using this observation. And so the issue that
this train, right? This is assuming this is coming from the true d of x, right? Because this p theta train is a distribution over xy pairs. So to simulate this, you actually need to use d of x, correct?
No, I have true samples, right? So I can pick one of my training samples is already a sample from this model.
But p theta train, right? That's a function of theta star.
Correct.
And your I see. Sorry, that's the truth. Okay. I see. Sorry.
This is the truth. This is the fake, and I have to simulate that fake
I see.
to get this other term. Mm-hmm. But this simulation has to be successful, and because of the training, because of the truncation, that's not to be taken for granted. So I have to be very careful where I'm doing stochastic gradient descent. If I go to thetas that are very far away from theta star, it's possible that so I'm going to simulate this model doing rejection sampling. So I'm going to pick an x, and then I'm going to run it through my model, and then I'll see if it successfully makes it into the observation window. If that process fails over and over again, I won't be able to simulate that sample. So I better make sure that my stochastic gradient doesn't wander too far away in space, and that it successfully and that rejection sampling succeeds. And the other thing that I need to have strong convexity, so that if I make likelihood small, I can also argue that I have learned in parameter distance and not just in likelihood value. So that's kind of like these are kind of the components that you need to get the end-to-end results. But if you just have a neural network in there, you can always just do stochastic gradient descent by just exploiting this very simple idea. Let me skip this result and show you some NBA data example. So these are the NBA. This is all the NBA data from after year 2000. These are the heights of basketball players, which are a nice Gaussian around 2 meters. And these are the number of points per game scored by these players. If you do linear regression on this data, I'm not claiming that's the right thing to do, but if you were to do linear regression to relate height to number of points per game, you get this decreasing negatively sloped curve. So here's a nice test that I'm going to do. So I'm going to truncate this data even further. So I'm going to look at players who score at least 8 points per game, which is this data. Now, if I were to be naive and say, look, okay, so now I'm doing truncation on the truncation. Okay, so if I was naive and tried to fit a line, I would get this line. Okay. If I don't take into account the fact that I've done truncation at least 8 points per game, I get a positively sloping curve. So if I do least squares regression, but if I take into account the fact that I truncated at 8 points, I will recover a negatively sloping line. Okay, this is the benefit of thinking about the fact that some truncation has happened already in your data. This is certainly not a line you would fit if you thought this is your data set. But if you think that this data set was produced by truncating a different data set, then this line now makes sense. That's the maximum likelihood line. Okay? So I don't have too much time left, but let me discuss. I another type of truncation statistics problem that better fits to the gender prediction story. So in that, I have 1 minute, right? Yeah. According to my timer. In this setting, what I'm doing is I'm going to assume that the world is produced as follows. There is an underlying distribution D that samples images and their label. But then an unknown mechanism looks at the images and decides whether or not to include those images and their labels in my training set. Okay, so in particular, for example, it could be that this phi, which is unknown to me, looks at the race, the skin tone, etc. of that person, and depending on that, decides whether or not to post that image on the internet. Okay, give it to me for training. So given filtered data like that, and given and that's an extra thing that we assume, given a big test set that now is the test that I'm interested in. So I have a training set that is biased, and I also have a test set that is not biased. The test set has, like images of all sorts of people. These are really the images that I'm interested in labeling. Okay, so I'm given a biased but a labeled data set, and I'm given an unbiased but unlabeled test set. So what I want to do is I want to get a gender classifier that does well in the unbiased distribution.
So just so that I understand, why in this case don't you do importance weighting?
You have to do some kind of importance weighting. The problem is now you don't know the criteria based on which the adversary decided whether or not to include the images in your data set. So in this case, you don't know the filtering
So what's going to be the assumption?
procedure. So the assumption is that you're given a labeled and biased data set and an unlabeled and unbiased test set.
Then can I learn?
So you have to learn this filtering procedure and then do likelihood based on that, which is what the maximum likelihood setting we propose does, and it's an alternative to several other domain adaptation approaches. Okay. Here's one example, and I'm going to close with that. So here we did the following experiment. We took images, and we looked, and also a very good gender classifier, and we looked at the images where the gender classifier fails. Okay, and here are some images where the gender class. These are some hard male images. So this is where the really good gender classifier fails. These are easy male images where it's successful. These are hard female images where it fails. These are easy female images where it does not fail. So we took a very good gender classifier, and we looked at where it fails and where it does not fail. And we created a data set that predominantly contains hard images and contains very few easy images. And we gave that as a training set to a gender classifier. So now, if you are naive about it, if you train on that biased data set, where kind of like the roles of male and females have been reversed, you start at a random guess, and you slowly become worse and worse and worse in the unbiased data set. Because you really learn a flipped world. Well, if you take into account that there is a possible truncation, you can recover from that problem. In any event, so this is another thing I want to talk about, which is it's an unsupervised learning problem where you learn densities.
Can you, by the way?
Oh, sorry.
Sorry to do this, but so this is the probability of correctness on the unbiased data set.
Correct. Yeah.
So you're still doing very badly compared to the algorithm. I mean, you're getting 55% correct in the corrected case.
We're slowly improving. Yeah.
Maybe you get there.
Well, I haven't saturated yet. So. So we have some results on unsupervised learning densities. Again, what we get is that we, get optimal rates for learning Gaussians and exponential families as a function of the dimension of the data. But in summary, so the line of work and the examples I gave, are an approach of using censored and truncated statistics to remove bias that enters because your training set is not representative of the conditions that your algorithm will encounter in the future. How can you learn things that are robust to the fact that there is a selection bias in how you obtain your data set? Okay? So we have, again, a general framework that works for neural nets. It's based on SGD. But if you want to get end-to-end guarantees, we can provide those for several old problems in statistics, in particular truncated linear regression, probability logistic, and Gaussian learning truncated Gaussians. So that's it. Thank you.
Quick suggestion. Can you go back to the slide where you had the basketball truncated by Y?
Can I or?
No.
I remember the picture. Yeah.
Because there is a much simpler algorithm.
Yes. Which is? I mean, so truncated linear regression is an old problem in statistics that is unresolved. So
the main point is that epsilon is symmetric, and I would like to reflect half the points to below your current estimate.
That's not going to work. Because you cannot reflect all of them. You don't know where the line...
No, don't reflect all of them.
If you knew where the line...
50% probability I reflect.
If you knew where the line is, that would work. But you don't know where the line is, so...
No, I'm doing literally.
You good?
Okay.
Yeah.
Next up we have Tengyu Ma from Stanford.
Can you hear me? Is this working? Okay. So I'm going to talk about the regularization effect of initial large learning rate. And this is joint work with Yuanzhi Li, I think who is still technically at Stanford, but he's going to CMU for his job. And also Colin Wei, my student at Stanford. So, and Tengyu Ma. So I guess we're going to talk about regularization. However, I guess the motivation, at least the original motivation of this project was about faster algorithms. So I think 2 years ago, I decided to join Facebook for a year, and I was thinking that I wanted to design faster algorithms, empirically faster algorithms for deep learning. So probably 3 years ago, we with Elad, Hazan, and many other collaborators, we designed different kind of theoretically faster algorithms for non-convex problems, and I was thinking maybe I should try some of these for deep models. And then I tried a little bit, and they didn't work. And then I realized that somehow a little bit interestingly, so actually if you just want to have faster training, it's not that difficult. So what you only need to do is to use a smaller learning rate. And that's so easy, right? So this is give you faster training. And however, the catch is that the test accuracy wouldn't be as good as large learning rate. So here is a plot I produced 2 years ago. I couldn't change the format because I don't have access to the Facebook cluster anymore. So let me parse this. So the orange ones are the training and test of an algorithm with initial learning rate 0.1. This is with initial learning rate 0.01. 0.01 is considered to be like small in this case. And the green ones are the curves from an algorithm with initial learning rate 0.1, which is considered to be a large learning rate. And you can see that in terms of training, the dotted line are the training curves. And the training performance is much better for the small learning rate one. However, the test performance at the beginning, the test performance of the orange one, the small learning rate one, is better. But at the end of the day, after converging, somehow the green one beats the orange one. And if you run it for longer, you never see that the orange one can catch up. So somehow, just intrinsically, there's something happening here with the large learning rate. So large learning rate helps us to regularize so that at the end of the day, we have better test accuracy. So this is not even about how fast we converge in test accuracy. This is really about even the final accuracy for the large learning rate one is much better. It's a little bit better than the small learning rate one. Here, you only have 1% improvement, but depending on the data set and settings. So here, the improvement is only 1% just because we are using all the state-of-art kind of like architectures and regularization, so you cannot hope to have much improvement. But if you don't have, for example, data augmentation, you will see the gap is very big. So this is in one sense this is really nice because we see something new, a new phenomenon here because the algorithm can regularize. I guess Nati has talked about it, and many others have talked about the regularization effect of algorithms. However, so this is really exciting. It brings us it opens up a lot of new research directions. However, on the other hand, the kind of the worry is that at least the bottleneck seems to be that we don't understand the regularization effect of the algorithm, so that we don't know how to design better optimization algorithms. So because I may find a better optimization algorithms that train faster, but if I run it, if I don't understand regularization, very likely outcome is that I run it on the real data set and the generalization is not as good. I guess I think I talked to Leon at some point at Facebook about this, and Leon told me actually they have tried this probably like 20 years ago and found that second order algorithm can train faster, but the generalization is not as great. So and also so this plot is not just created by myself. Like actually many papers have reported it. I was just kind of slow on kind of reading those papers. That's why I discovered it myself. But actually, they reported much earlier this effect. So I guess the main question I want to answer, at least we can try to partially answer in this talk, is that why large initial learning rate can help generalization. And hopefully, if I understand this, we can design better optimization in the future. So if you think about it, it's not that simple because the only thing matters here is the initial learning rate somehow. So somehow, because the initial learning rate makes a difference, somehow this analysis has to be somewhat history sensitive. So the analysis of the algorithm has to depend on what happens at the beginning stage of the algorithm. And this means that it's not that easy to find a simplified setting that you can see such a phenomenon. For example, if you work with linear models, then linear models very likely, I think we are almost sure that linear models wouldn't have this property. So first of all, with regularization, this is a strongly convex problem. So it doesn't really matter what algorithm you use, so there's no regularization effect. And when there's no regularization, depending on what laws you are using, if you use logistic laws, I think Natis and his collaborators' papers have shown that the iterate of the SGD doesn't depend on actually initialization. It only depends on the final learning rate. And if it's square laws, I think roughly speaking, I think the same thing happens. So here, because everything is convex, we kind of understand the iterates, and I'm very confident that there's no such phenomenon here about the initial learning rate. And often the final learning rate is what matters. And sometimes initialization matters a little bit because if you're initializing the off subspace of the orthogonal subspace to the data, then you are not going to change anything there. So that's why initialization matters a little bit. And also another kind of, at least difficulty for me to study this problem was that you cannot just talk about the limiting behavior for the same reason, because what happens is not, what matters is not at the end, right? So what your learning rate you use. So we cannot just take t to infinity and studying the limiting behavior of this stochastic process. And NTK is also not really helping here because NTK is pretty much a linear model. And with convex optimization in kernel space. So it falls into the first category. So the work we are doing here is that we found a toy data distribution, and for two linear networks, for this toy data distribution, we show that actually this phenomenon occurs, and the reason that it occurs is that SGD learns various different patterns in different orders with different learning rate schedules. So what the learning rate schedules matters is that it learns different patterns in different orders. And because the orders are different, we'll see that this results in different generalization performance at the end of the day. So, right, so what other type of patterns we're talking about? So first of all, I'm only going to construct a kind of contrive the data distribution for which we can theoretically analyze this. But at the beginning, I'm going to give the bigger picture on what kind of constructions we're going to do. So we're going to construct two patterns. So the first type of pattern is what we call hard to generalize but easy to fit pattern. So these are, in this setting, for example, you can think of as linearly separable, linearly classifiable patterns. So so this is simple to easy to fit because you only need a linear model, a very simple architecture to fit such data. But you at least requires the same dimension number of data points to generalize. So and this is what we call hard to generalize but easy to fit. And the other type of pattern in comparison is easy to generalize and hard to fit patterns. So we are going to use this concrete example where you have, for example, a cluster data. So like say the data points are clustered into 3 groups. And these 3 groups are in a line. So, and these are positive examples. And these are, in the middle, we have negative examples. And in this case, you cannot have a linear separator to separate all the data because the 3 clusters, is in a line. So there's no linear classifier. So that's why we say it's hard to fit because you need at least a 2-layer network to fit such data. But because they are very tightly clustered, actually the generalization is easy, even though you need a 2-layer network, because the only thing you need to do is to pretty much memorize the 3 points, right? The 3 center of the cluster, and then basically after you see 3 examples, you can generalize perfectly. So so it requires a complex model, but very few samples to generalize. And these are the 2 types of patterns we are going to talk about, and we're going to show that learning order in some sense matters when the distribution have different type of patterns. So here is the how do we construct the Taylor distribution with mixed patterns. So so our data point would have 2 subsets of coordinates, and the first subset of coordinates is called x1 is of dimension d, and the second subset of coordinates is also of dimension d, and so we're going to construct 3 types of examples. This data set is going to be heterogeneous. So the first type of example has 20% of mass, and this 20% of examples are of the form x1, 0. So the second pattern doesn't exist, and we only have the first pattern. And the first pattern is generated from the first pattern, the linearly classifiable patterns. And type 2 examples have also 20% of mass, and they are going to have no first order, no first pattern in the first set of coordinates, and the second set of coordinates will be generated by the second type pattern, clustered but not linearly separable patterns. And the third type of examples are the rest, and they have both of the patterns. So the reason why we care about this is that with this heterogeneous data set, you can see the learning order make a difference. So we're going to compare 2 algorithms. So the first algorithm is going to learn the first type of pattern first, and then learn the second pattern. So basically, it first learns pattern 1, and what you do is, how do you learn pattern 1? So basically, type 1 example and type 3 example have both, x1 in it, so you can use all of them to learn pattern 1. Question?
So pattern 1, you require them to be linearly classifiable only, or you also you want them to have high variance, not well clustered?
So we do. So for type 1, we do want them to be high variance. So
okay.
I will talk about exact construction. So basically, you can think of these 2 as some half Gaussian, so that it requires at least a d number of samples to generalize. Right. So
what is the meaning of x's and circles?
So x's are the positive examples, circles are the negative examples.
So x1 it contains the label as well.
So I'm. Yes.
There's an extra label coming together with
Yes. So there's a label associated with them. I think I will be more precise in the next slide, but just explain here real quick. So by x1 generated from pattern 1, I mean I generate x1 and the label together from this distribution.
The label is inside x1 or it's associated with the
label is outside x1, technically in terms of notation. Yeah.
Inside x1.
Outside.
Outside.
Yeah. Yeah. So technically I should write x1, comma y generated from pattern 1.
Okay. I see.
Yeah.
So when you say in the third type x1, x2, you have two labels.
I have one labels and they are coupled. So x1 and x2 are generated from the same label.
I see.
So you condition on a label and then you generate x1 and x2. It'll be more clear in the next slide. All right. So going back to the learning orders. So if you have such a heterogeneous data set, then if you want to learn the pattern 1 first, then what happens is that you should use all the examples with pattern 1 to learn pattern 1. So basically you're going to use type 1 and type 3 data where there are x1s in them. So and you find the best linear fit, right? And then so we can learn pattern 2. So let's say when we learn pattern 2, we just use the rest of the 20% of examples where there are only pattern 2, right? So algorithm 2 has a different order. So what you do is you learn pattern 2 first, where you find the best nonlinear fit to all of those examples with pattern 2, right? So what examples have pattern 2? Type 2 and type 3 examples would have pattern 2. And then you learn the rest. And now there are only 20% of examples left, right? Because all the type 2 and type 3 examples already fit perfectly. So there are only 20% of examples left. They are type 1 data. So basically the difference here is that in terms of learning pattern 1, here in the first algorithm, we are using 80% of the data with the pattern 1. And in the second case, we are only using 20% of data because the rest of 60% was used to learn pattern 2, and they are fit exactly, and you cannot use them anymore. So, and suppose this is what happens with large learning rate and small learning rate, and you can see that there will be a difference in terms of generalization because here the generalization would be better because you are using 80% of the data, and here the generalization would be worse because you are using only 20% of the data. And here I'm only talking about learning pattern 1. Learning pattern 2 is always good because pattern 2 is so easy to learn. You only need 3 examples to learn pattern 2, so it's out of the question. So both of the examples could learn pattern 2 very well. So basically what we're going to show is that this large learning rate plus annealing is going to do algorithm 1. It's going to do exactly these two things. And a small learning rate throughout would do the algorithm 2. So that's why algorithm 1 and algorithm 2, or small learning rate and large learning rate, would have a difference in generalization performance, just because their generalization performance in pattern 1 for pattern 1 are different, because they are learned from a different number of examples. Any questions so far? So this is just a high-level plan. I'll tell you a little more about how do we exactly construct this and prove them. So. So I guess also let's just do a sanity check, whether we have any history dependency here in terms of analysis. And we do because the use of logistic loss. So basically what happens is that when you use large learning rate and annealing, so you're going to learn pattern 1 first. And now after you use up all of this data, because we are using logistic loss, after a sample is fit, then because the confidence is so high and the gradient is so small, so you can never use them really for anything else. Or at least in a long time, you cannot use them unless the confidence job come back. So pretty much after you learn some examples with logistic loss very well, then you cannot use them anymore. So that's why here, after you learn pattern 1, you cannot use those examples to learn pattern 2, and the same thing happens here. So that's how the history dependency comes from.
So there could be, I guess that's not the point, but there could be other things to fix the issue of this example, right? You could have a constant learning rate and do, for instance, dropout or something like that.
Yes. You will see we have some mitigation strategy which is very close to dropout. So I guess I'm going to talk about mitigation strategy at the end of the talk. And here this is an experiment that shows that on artificial data set, artificial real data set, you can also see this kind of phenomenon. So what we for artificial synthetic artificial data set. Okay. So anyway, so what we can prove is a very toy case. And here, this is a little bit more realistic case. It's still not a real data set, but it's a little bit more realistic. So here is how we generate data set. So you want to kind of like so the idea is that we want to say that in a real data set you also have this easier pattern and hard pattern, or like these two types of patterns, but we couldn't find them. At least we don't know how to find them yet. So what we did is that we say all the patterns in the existing image, they are type 1 pattern, and we kind of just inject type 2 pattern, those kind of easy to generalize but hard to fit pattern. So how do we do that? So basically, we just say we add this kind of watermark in the middle of the CFAR image, and this is the type 2 pattern. So basically, for every class, you have exactly 2 patches, and these 2 patches are just exactly associated to that class. And if you see that 2 patterns, you know exactly which class they are. And you just inject those kind of 2 patterns for all the images in that class. So you inject one of the 2 patterns for all the images in that class. So basically, we have 2 patterns vi and vi prime for each class I, and we put vi or vi prime in the examples with class I. And we also kind of use the same kind of like this type 1, type 2, type 3 kind of construction. 20% of examples doesn't have any patch, and 20% of examples have only patch. So you don't have even any real image. It's just a patch in the middle and with like a 0 background. And 60% of examples are mixed. So, and now we have a data set, and we can run experiments with large learning rate or small learning rate and see what kind of patterns we are learning.
20% is just like duplicate a single image, essentially.
Yes, 20% are just clean image. Yeah. So, and now we just run this large learning rate and small learning rate example on this data set, and we want to see whether we learn the patch first or we learn the real image first, right? So we want to, so in this case, because we know what our patterns are, we can examine how what's the learning order of these patterns. And I'll ask you to ignore the green one because this is actually the mitigation strategy. So let's just focus on the blue and the red one. So the blue one is large learning rate plus annealing, and this is the point where we anneal epoch 30, and green one is just a small learning rate throughout. Oh, sorry. I'm going to ask you to ignore green, and the red one is small learning rate throughout. So, and you can see that when you look at the clean accuracy, the accuracy on the clean examples, the blue one, right? So the large learning rate plus annealing, it does get very good clean accuracy. So, but the clean accuracy for the small learning rate one is not as good as the clean accuracy for the large learning rate one. So this is according to our explanation, this is just because you are not using enough samples to learn the clean pattern, the pattern 1 with small learning rate. And we can also see, maybe this is more informative, if you look at the patch accuracy. So here what we mean is that we just give the patch to the classifier and see what's accuracy. So this is kind of like measuring how much you learn, how much you are using pattern 2, the patch, to classify. And now this is pretty kind of clear. So when you use small learning rate, you are going to learn the patch very, very quickly. So the pattern 2 is learned very, very quickly in 5 epoch. However, if you use large learning rate, you are not going to learn pattern 2 until you anneal. So basically, with large learning rate, you are not just going to ignore the patch in the middle because you somehow detect that this is a spurious kind of pattern.
So your definition of clean accuracy, what is that precisely? So
you just apply your model on random clean examples.
Without the watermark.
Without the modification.
And it's the same unconditional distribution. You want?
Yep, the same unconditional distribution.
Okay, and then the patch accuracy, you're including the watermark?
The patch accuracy is we just exclude, we just only have the watermark and 0 background. Background is just set to 0.
Oh, so you only have the watermark?
Yes.
And that's versus images that are just all white or something? Or?
Yeah.
Okay.
Yeah. So I think if you can still classify that correctly, that basically suggests that you are learning the patch. Because you are not given the image, actually. You only given the patch.
But you're comparing it to like all white images or something? Or
all white image would give 0 accuracy, right?
Right. But I'm saying, so there's only one type of image in the patch accuracy?
there's only one type of images. Yeah. So basically, you just have like 20 images because for every class, there are 10 classes. Every class there are two images. You only have these 20 images and and look at what's accuracy there. So with large learning rate, you are going to ignore the patch basically, and with small learning rate, you are not going to, or you are going to learn the patch very quickly. So.
Why do you have two patches for each class? If I had only one patch per class?
I think then it would be linearly classifiable. So I need the patches to be kind of on a symmetric position so that the patches cannot be linearly separable. This is also in our construction as well. And I think we did try one patch and it didn't work. So large learning rate doesn't learn the patches, and the learning the patches early hurts the generalization of clean images, because with the right curve, you learn the patch very early, but you don't learn the second pattern that well. All right, so I guess probably I have about 10 minutes, or less than 10 minutes?
Like 6 minutes.
6 minutes? Okay, so then probably I will just go very quickly about, I'm not saying too much here actually. So basically this is just the exact construction. So here I'm using the right notation. I'm going to generate x1 and y from the distribution P. And distribution P, pattern 1, is going to be just a linearly separable 2-half Gaussian with some margin. The exact details probably don't matter. And at type 2 are, you generate from the second pattern, which is kind of like this. So we construct it so that they are not linearly separable. And they are clustered in terms of the directions. So, and the type 3 is basically you find a way to generate. Basically, you couple the label so that jointly, x1 y is from P and x2 y is from Q. Basically, you conditional label and you generate x1 and x2 from the conditional distribution of the data conditional label, right? So these are the settings we can prove theorems, and I think the important thing is that this is not linearly classifiable. So that's why we have these two clusters for label 1, right? So that they are not linearly classifiable. So I guess I'll probably kind of like skip the theorem statement. The statement is pretty much what I kind of have told you. I just make it a little bit more kind of formal, but still not very formal, because I'm going to sweep a lot of things under the rug. So I guess the important thing is that we are going to use some architecture that are not exactly the standard architecture, because this is the only place where we can prove it, the only cases where we can prove it. So we need that architecture to work on x1 and x2 independently in some way. And also the algorithm we analyze is with Gaussian noise. So the noise come into play, which I'm going to talk about in a moment. And then we can prove that algorithm 1, large learning rate plus annealing, can work, and algorithm 2 doesn't work. Given I have not too much time, let me not get into details here. So I guess I want to talk about the basic intuitions a little bit, because I think that's probably the most interesting thing here. So in analysis, when we have small learning rate, what we do is basically just say this is kind of NTK. And with NTK, you can analyze the convergence, you know how fast it converges, and so on and so forth. We need to do a little bit more work on top of NTK to exactly characterize which patterns we learn. And what's interesting is about the large learning rate. Why with large learning rate you are not going to learn pattern 2 with large learning rate? And the reason is the following. So when you use large learning rate, the noise is very big. Because when you have large learning, suppose you have the same amount of noise, large learning rate would so suppose you have the same amount of noise in a gradient, then large learning rate corresponds to effectively larger amount of noise in the iterate, and that means that the weights change a lot. So and when weights change a lot and the noise is big, so what happens is that if you look at your model on the second type of pattern, right, this kind of like a clustered pattern, so then actually your model cannot do really a full powerful two-layer network. Actually, your model can only behave like a linear model when the noise is big. So the reason is that suppose you have a vector W, and this W is not going to separate this cluster. So suppose this W is kind of like all the data points is on one side of the W. So that means that your activation pattern is going to be all the same for the three type of examples, right? Z minus zeta, Z and Z plus zeta. So basically, even though you have a ReLU of W transpose X, actually the ReLU is not doing much work. The ReLU is always giving you the fixed sign for all the pattern 2 examples.
Can I ask one thing? If you restate things, forget the choice of learning rate. Just give me in the first 20% of time steps examples from pattern 2, and then in the last 80% examples from pattern 1. Mm-hmm. So then you're saying no matter what, any algorithm is going to do bad because it will.
No, I'm not saying that.
What I meant is that the learning rate doesn't really matter in that case.
Yeah, you are right that the learning rate doesn't matter in that case, and but we couldn't prove that no algorithm, whatever you can do, all algorithm will be bad. We can only prove that a certain algorithm will be bad because your algorithm has to kind of use up the first batch of examples.
When I said all algorithm, I just meant that the learning rate will not help you if you just give me first 20%, first pattern 2, and then pattern 1.
Yep. So, but the hard part is that, yes, that I agree, and it's not that hard to show that. The hard part is that to show the learning rate can give you the right order, right? Large learning rate give you the right order, and small learning rate give you the different order. So that's the technical difficulty. All right. So and here basically I'm trying to say that if you use a large learning rate, you are not going to learn pattern 2, even though you are given pattern 2 in the algorithm. And the reason is that the weight is too big, and the weight is too random, so that you never behave as a nonlinear function. So it's basically the neuron is always kind of like a linear function. So the neuron satisfies something like this. You look at these 2 points and you average them, and it's actually equals to the points in the middle. So you always have a linear function. So that's kind of why you cannot learn this kind of patterns, because they are not linearly separable. And only when you anneal the learning rate, you are going to reduce the noise level so that you can see some W that can create a hyperplane that is in between these example clusters, so that you can have a nonlinear model on this data distribution. And that's the key intuition. So I guess I'll skip some of the technical intuitions. I guess this is probably recorded if you're interested. So I guess let me talk a little bit about the mitigation strategy. So our theory suggests that if you use large learning rate, you inject a lot of noise in the activation pattern. And that prevents us to learn the easy to generalize pattern, because if you have a lot of noise in activation pattern, you behave like a linear model. And we try to see whether this can help us to kind of like design a mitigation strategy. And the natural mitigation strategy is just that you add noises in pre-activation, so which is kind of like dropout. So now we can talk about the green one, which is basically small learning rate plus noise, right? So now we have small learning rate, but we use noise to prevent us to learn the spurious artificial pattern. So now you can see that the green one with noise wouldn't learn the artificial pattern with even small learning rate, and you anneal the I think here you anneal the noise level, and then you can learn the pattern, so that you can get a little bit better accuracy. So this is indeed a mitigation strategy, and also we tried this on clean data without the artificial patch, and actually it still helps improve the accuracy when you have a small learning rate. So basically, here is the experiment on CFAR 10 with some white rise 16. So I guess this and this are the baselines. So large learning rate plus annealing, that's 90%, and small learning rate we have 84%. So there's a 6% gap between large learning rate and small learning rate. And if we use small learning rate plus pre-activation noise, we can recover that gap by pretty much most of that gap. By the way, these numbers are not that high just because we don't have data augmentation here, so that we can see the gap between these two are 6%. If you have data augmentation, then the gap between a large and small learning rate is probably like 2% or something like that. Yeah. So okay. So I guess just to wrap up quickly. So the main message is that large learning rate learns hard to generalize, easy to fade pattern, and small learning rate learns easy to generalize and hard to fade pattern. And orders to learning of learning these patterns do matter with logistic loss. And I guess the open questions are that how do we identify these patterns in real data? We don't know how to do it yet. We try to inject it, inject artificial patterns, but we don't know how to identify these patterns in real data. And how do we make the results more general instead of only on a contrived toy example? So this example is really toy, so we don't have any ideas how to prove that. So, and finally, the last slide, I'd like to share some of at least my personal broader outlook about algorithmic regularization. So I guess, this work is kind of under the broader kind of scope of algorithmic regularization, and at least, maybe it's just me, like us, we couldn't prove, stronger results, but it sounds like understanding algorithmic regularization is very challenging because even on these toy examples, we need to spend like 40 pages or 50 pages to prove everything. And also, it's not clear for these toy cases what complex measure the algorithm is regularizing. So it's really kind of complicated. So, so in some sense, I'd like to also kind of like, at least draw us to think about, one other possible shortcut to kind of like deal with these kind of things. Like, maybe, suppose I'm being pessimistic, maybe one thing, we couldn't, make very, very, big progress in terms of understanding algorithmic regularization in the near future. But it could be that another route, which is a little bit cheating but easier, is that you can say we can find explicit regularizers that can subsume the algorithmic regularization, at least empirically. So that so we design explicit regularizers and we run the explicit regularizers on a real data set, and we hope to see that you don't have to use the algorithm to regularize. And now this at least solves the optimization issue, because now with this regularizer I can safely design a faster algorithm. I have the separation of concern. I only have to care about I have a faster algorithm, but I don't have to think about whether my regularization is enough or not from my algorithm. And we have seen some initial preliminary promising signs from using some of this data-dependent regularization. So these are regularizations which doesn't only depend on the norm of the parameters, but also depends on other quantities in the network, for example, activations and other things. So, and also the final point I'd like to make is that generally I suspect that the heterogeneity of the data sets are something that is important. So we can see here the interesting phenomenon occurs when we have a heterogeneous data set. And also, I suspect that in general, probably when you have heterogeneity in a data set, the practical improvements are also somewhat kind of easier. I suspect that probably standard data sets, when everything is designed so nicely, so the data set is already well tuned for algorithmic regularization, so it's very hard to see whether explicit regularizers can improve the accuracy. For example, when there are imbalanced data sets, we found that explicit regularization actually could help a lot in terms of practical performance. We have this paper that has very simple theory, like the theory is kind of as easy as homework questions for a class, but the empirical performance is much better than the previous state of art. I guess that's all I want to say. Thank you.
So I think we should take the questions offline, and then let's all go to lunch.